Do you see my screen?
Yes.
Okay, so first I want to say thanks to the ICPRS for this opportunity and for this space. My name is Daniela Diaz, and I'm going to present you our article named Aromatic Method for Detecting Specular Reflection and Motion Blur Artifacts on Endoscopic Images using Complementary Binary Classifiers. Let's start by knowing the definition of an endoscopy. It's a non-surgical diagnostic imaging tool mainly used in digestive disease diagnostic, where an endoscope is inserted into the body to look inside an organ or tissue. An endoscope, it's a tube with a source camera and with a source light and a digital camera transmitting a large number of images into a monitor. Those images tend to be corrupted by multiple image artifacts, like those listed on the right. An artifact is defined as the distortion or addition of error in an image that has no correlation with the anatomical region studied. Those artifacts can compromise between 30 to 40% of the images, and in the case of motion blur, that value can reach to 25% of the images. Artifacts decrease the image quality, make harder to see abnormalities, and last but not least, affect the performance of computer-aided diagnosis tools. That's the reason why we present a pre-processing tool for identifying the most frequent artifacts on images like motion blur and specular reflections. Motion blur may be a result of a camera fast movement or the frequent camera focus changes while it's moving along the digestive tract, resulting in loss of edges or loss of visual tissue information. Specular reflections occur when the energy is concentrated in a small lobe, leading to strong highlights on the image. Their shape and size can vary, and they are randomly distributed on tissue surfaces. Specular reflections have high brightness and low saturation. To achieve this article proposal, our methodology includes a preprocessing step in which each image is intensity normalization and each image is contrast enhanced. In this stage, there is also array detection for avoiding any acquisition or clinical descriptor marks. There is also a feature extraction where intensity and texture descriptors are extracted for the image for detecting the presence of, for detecting the particular artifact on an image. Finally, the expected features are filtered using univariate statistical methods, and those selected features fit two complementary binary classifiers. First, let's talk about the database. For this study, images from the endoscopic artifact detection challenge were used for training and testing the proposal strategy. The data was obtained from 6 different acquisition centers, contained multimodal endoscopy sequences, and multi-tissue endoscopy video frames. The whole database consists of 7 artifact classes. However, in this study, we only used motion blur and specular reflections. The dataset was divided into 3 batches: training, testing, and blind evaluation, as you can see in the table. We also had 135 control images for specular reflection segmentations. In the preprocessing step, 3 major tasks have to be addressed. First, intensity range normalization. Second, contrast enhancement. And third, ray detection. As we saw before, different types of acquisition of the images can affect their intensity values. So all of them have to be mapped into a common intensity range. For doing so, a min-max linear normalization is applied to the images in order to have a new image with an intensity range set to 0 to 255. There is also an adaptive equalization, which is done with a contrast enhancement, which is done with an adaptive histogram equalization with an A-per-A kernel to strengthen the artifacts of the background of the image. There is also a new color space selection to enhance differences between concerned artifacts and the interstitium. So channels B from RGB and S from HSV are chosen. Finally, the ROI is carried out in order to limit the artifact search space and eliminate certain labels that may appear on the endoscopy images. For doing so, the images are transformed from RGB to XYZ color space to highlight the differences between tissue and added labels. Then a binary mask is calculated according to a threshold which is set to the 30% of the maximum intensity value of the cumulative distribution function. Finally, morphological operations like opening and closing are applied to the region selection. Once the ROI is carried out, there is a segmentation and candidate selection process. For motion blur, the image is divided into 300 per 300 windows, and for specular reflection, the goal is to find the possible candidates and the bounding box position that contains the artifact. The specular reflection candidates are selected using local adaptive thresholding. For doing so, a binary mask is obtained by finding the threshold value that determines the brightest region of a sliding window histogram. Then, to expand and fill the gaps of potential candidate, morphological operations are applied to the mask. In the feature extraction process, different intensity and texture-based features are extracted from the complete image in S and B channels. As part of this process, 7 statistics from the Haralick's features are calculated, like homogeneity, angular second moment, contrast, entropy, correlation, energy, and dissimilarity. There is also a new texture metric called comparative Gaussian frame changes, and additionally, intensity features like brightness and intensity pixel deviation are extracted. Once all proposed features are extracted, a preliminary evaluation of its capacity to separate the 3 concerned artifacts, motion blur, specular reflection, and others, is done. For this evaluation, univariate quantitative tools are used, including T-student and Wilcoxon ransom test. These tests are applied for each of the features previously described, comparing the classes in the following way: motion blur versus specular reflections, motion blur versus others, and specular reflections versus others. In the first case of quantitative evaluation, the student seeks to find the feature that best succeeds to separate one class from other. That is when there is a significant difference between the means of their classes. That is to say, a p-value less than 0.05. Wilcoxon test is used to corroborate the student results, and this test tells if the medians of the class data distributions are equal or different. Additionally, those results are validated by analyzing the box plots and scatter of the features. At the end of the evaluation, the most relevant features were entropy, which is one of the Haralick's texture descriptors obtained from the grade level co-occurrence matrix. Lower entropy is expected in images with motion blur than with the rest of the classes due to the loss of visual information. Comparative Gaussian frame changes. It's a metric that takes advantage of the fact that motion blur doesn't have many high frequencies compared to normal tissue. So this metric takes the image that is candidate to contain artifacts and compares with its smoothed version using a structure similarity index metric. As you can see, this metric allows image texture assessment, taking into account that in the case that the input image doesn't contain motion blur, the metric will be low, close to 0. In the other case, if the input is a blurry image, the metric will be high, close to 1. Brightness tells the general lightness or darkness of the frame. As we have seen, specular reflection has most of its intensity distribution at the lightest part of the histogram. So higher brightness values are expected in images with specular reflections than with the rest of the classes. Contrast is also one of the Haralick's texture descriptors, and high values are expected in images with specular reflections than with the rest of the classes. Finally, intensity pixel deviations refers to the scattering of the image intensity value with respect to its mean. So it's expected greater scatter in the specular reflection intensities than in the other classes. As we can see in the tables, the p-values support the discriminant feature selection because all of them are lower than 0.05. In box plots and scatter diagrams are analyzed. In the first analysis of the box plots, the interquartile in each feature shows that it doesn't overlap with the rest of the classes, as we can see in the images. But this also reveals that there is no evidence of separability between the three classes. It only shows the separability between one class from the rest, as we can see in the scatter diagrams. For example, in the first diagram, we can see the separability between the red points, which are the features related to motion blur. There is a separability between the purple points, which are features related to specular reflection and others. This also occurs in the other three scatters, showing separability between specular reflection versus the others. As a result of the above feature evaluation, complementary binary classifiers emerge as a reliable options, since separability is only tested between one class versus the rest. So we are going to have two binary classifiers. The first one is going to identify motion blur versus the others, and the second one is going to identify specular reflection versus the others. In both classifiers, we used random forest classification, but the difference is that in classification A, we used 15 trees, and in classification B, we used 30 trees. The combination of the complementary binary classifier leads to a combination of possible results like those exposed in the table. We could have the presence of both specular reflection and motion blur in the image, no artifact presence in the image, only the presence of motion blur, and only the presence of specular reflection. The data distribution robustness and methodology performance are evaluated in terms of accuracy, precision, recall, and specificity using A-fold cross-validation. As you can see, in classification A, we got an accuracy of 74%, and in classification B, an accuracy of 95%. In all of the cases, we have a low standard deviation. The root curve is computed, and the area under the curve is also used as a performance metric, where the mean AUC for classification A is 0.82, and for classification B is 0.99, with a standard deviation of 0. These results are comparable with the state-of-the-art reported strategies that have shown the best performances in classifying the concerned artifacts. Finally, for evaluating the entire identification methodology considering multi-class performance, a blind evaluation of 528 images is used to fit the two complementary classifiers. As you can see in the truth table, we compare the labeled artifacts provided by the challenge dataset with the proposed method results, obtaining an average precision of 82%. In conclusion, this paper proposed a new approach for detecting the two most frequent artifacts on endoscopic images, specular reflection and motion blur, through customized image features and supervised binary classifiers. Additionally, the device multi-artifact identification scheme based on complementary binary classifiers provides an alternative to the commonly used multi-class problems presented in the state-of-the-art and shows a comparable precision detection for motion blur and specular reflection. Thank you very much for your attention.